Ellie Sansom. I'm a researcher here at Curtin University as part of the Space Science and Technology Centre, and I'm also partly funded by ICRA as well at UWA, and Curtin. And I wanted to talk to you today a little bit about planetary science and integrating not only geoscience, but astronomy and all the multidisciplinary aspects that kind of go into planetary defence. So if you haven't been here before, the Space Science and Technology Centre here at Curtin University is the largest planetary science research group in the Southern Hemisphere. We have over 30 researchers dedicated to planetary science, and we are on multiple, I think 15, 16 active space missions with collaborators in international space agencies, and we get to do some really good fun stuff here and taking geoscience into our solar system. So also when the solar system started, formed and evolved, we have all these small particles that mostly coalesced into our planetesimals. So there's a lot left over. We have a lot of asteroids and small objects in our solar system. And this is a picture I took from my PhD students gave my candidacy today. Sophie, just to be we found this absolutely amazing, beautiful graphic by I think it's Eleanor Lutz, nice. And it's actually in log space of our solar system. So we have the sun in the middle, and all the way out, we have trans-Neptunian objects all the way out here in green. We have inner planets, and the Earth is here on its orbit in blue. And in between Mars here in red and Jupiter, slightly pinker further out. So if you guys online, hopefully you can kind of see that okay. I don't have a pointer, it's too far away for me to reach. There's this kind of cyan greeny area, which is the main asteroid belt in between Mars and Jupiter. So there's quite a lot of objects in there. And there's some of them actually are able to, due to different interactions, have changed their orbits, and they do come and cross Earth's orbit. And these ones we call near-Earth objects, and these are the ones that we're slightly concerned about whether or not they're going to come and impact the Earth. So we want to actually talk about how the hazard by numbers. I might start with this plot over here on the right, is looking at size of the different asteroids that we know in our solar system, not just asteroids, but of near-Earth asteroids, the ones that have the potential to kind of, they're in near-Earth space and could potentially migrate or have cause problems to the Earth. We have the KT impact up here at about 10 kilometers, so that's the dinosaur killer. And then we have down here the Chelyabinsk meteor bolide event. If anyone really remembers that back from 2013, there was a really, really big asteroid that came, well, big in our lifetime, asteroid that came through the atmosphere and exploded, and the shockwave from that shattered all the windows in the nearby area, and actually really caused quite a lot of damage. There's over 1,600 people injured. There were no deaths, luckily. And I think it was around 1.5 million Australian dollars worth of damage to infrastructure. So although these are classed as kind of not really a problem, there is this kind of residual risk zone of objects. So these are how many we think there are, and this is how many we know of. So obviously big ones that are going to completely destroy civilization. We know where about 98% of those ones are. This little dip doesn't exist anymore. This is still 2017. We've filled this in quite well up here. But down in this region, in the smaller 10 meters to 100 meter sizes, we can't see them with telescopes. They're just too faint to be observed by telescopes, but they're too rare to impact the Earth to get a really good idea of their frequency and how many there are. So I guess that's what this plot's showing over. This figure over here is a really nice picture from the DART mission brief, which talks about, obviously 10 kilometer side asteroids. We know where 100% of those are, fantastic. But as you get down to these kind of 25, so the Chelyabinsk meteor was 17 to 20 meters across. So that's the one we're talking about here. We're at 0.4% of those. Although we've only seen one event in the last 30 years. The uncertainty on that is it could be every 50 or it could be every 15. Now that's, in terms of geology and science, that's within the order of magnitude. Fantastic, but us as humans go, well, that's a little bit worrying that it could be between 15, it could be as often as every 15 years. So this is actually quite a big topic now around the world. Planetary defense is understanding the near-Earth object population. The US produced this in April this year, National Preparedness Strategy and Action Plan for Near-Earth Object Hazards and Planetary Defense. And in their table, goal number one and number two is characterization of near-Earth asteroids and near-Earth asteroid modeling and prediction. Those are two things that we can. I'm skipping ahead of myself. So asteroid characterization involves looking at their composition, what are they made of, geochemistries. We can't obviously get out there. We can look at their spectra through telescopes. How are their dynamics? How are they actually moving around our solar system? What are their physical properties? What are their strengths? And things like that. And yeah, we can do that from ground-based observations and radar facilities. And this is quite a nice plot that shows the how many objects or the mass of objects in the area versus semi-major axis. So that's distance from the sun. So the sun's over here. Earth is at 1 AU. And this is the main asteroid belt. So this is just looking at the geochemistry of the really large, or the main asteroids in the asteroid belt, not necessarily near Earth objects. And it's quite, there's a lot of information in here, but just showing that we do have kind of an idea of where different compositions are in the main belt across these larger bodies. And we can use that to kind of infer, which is more back to the sciencey side of things, of how mixing might have happened in the early accretion disk and look at mixing in our solar system through time and inform us about maybe LHB models, late heaven models, or GravTAC model, and things like that, to try and get an idea of where we are today. But also we can do that from meteorites. Meteorites are pretty much all examples of these asteroid bodies. So we can actually take the meteorites that we have on the ground, take them to the lab, look at their geochemistry, and how do they come to Earth? Got in the main belt, you might have a collision between two large objects. You could get a sample from an asteroid core, which will give you an iron meteorite, or something from a crust, which will give you something a little bit more like Earth's crust that come to Earth. We can do the geochemical analysis and get an idea of what these rocks, what these asteroids might be made of. And I forgot to let the video carry on with the another way of doing that is obviously sending out sample return missions as well. They're much more expensive, and they can only bring out back really small samples from a really small number of asteroids. And I'll come back to that in a second. The other part in that, what we're trying to look at for near-Earth objects is looking at the modelling and predictions. So we want to look at how we possibly disrupt asteroids in the future, and how can we assess the risks associated with the impact of asteroids on Earth. And we can do this from on Earth or on other planets from meteoroids coming through the atmosphere. We can get an idea of how these things break up in our atmosphere, gives us an idea of their strength, what might happen when they not necessarily come to Earth, but if we wanted to try and disrupt them out in space, what might that happen? We can infer that from fragmentation models here using our own atmosphere. This is a picture of the moon, and when meteoroids and asteroids hit the moon, they actually create what we call lunar flash. And it's actually some millisecond long events, but it's actually basically we're seeing impact events. We're using planet scale detectors. And then on Mars, this is an example of a cluster crater on Mars, where something has fragmented in the Martian atmosphere and left multiple craters on the ground. We don't see cluster craters really on Earth because the atmosphere destroys most of the smaller ones. But there are about 50% of the new craters on Mars over the last 10 years or so are cluster craters. So in terms of asteroid characterization, this is an example. So over here on the left, we have different types of asteroids, and on the right, we have different types of meteorites. So sorry, let me come back to the left-hand plot. I beg your pardon. In the middle here, we've got the meteorite. On the right here, we've got asteroids. And the meteorite type, this type here, L is one of the most. Sorry, I beg your pardon. LL is one of the not particularly common, but it's in there. This LL type corresponds mostly to S and Q type asteroids. So we've seen kind of things that don't match up there. So we have a problem with using meteorites to get an idea of what the large scale population might be of asteroids. And we're trying to figure out what that is. And one of the things here on this plot on the left is looking at the inner, middle, and outer solar system. These are different asteroid types. I wouldn't look at them too much, but what I'm just trying to show is that at different size ranges, these vary. So if you've got the really big things, you've got a different type of common asteroid. As you go to smaller things, that's changing. So obviously, as we go into meteorites, these are the really, really small objects that are hitting the Earth most frequently. And so that's why we're getting a mismatch between the two. So we can't necessarily just use meteorite population as a whole. We need to start looking at how these meteorites connect to their orbital space. Where are these meteorites coming from? And it's about we can actually do that by observing how they come in. And there's about 40 meteorites. Okay, there's about 70,000 meteorites in collections around the world that we can study. Fantastic. There's less than 40 that we have orbits for. So trying to give that spatial context for where they're coming from is really, really important. So yeah, we can do it by observing how they come through the atmosphere. And I'm not quite sure where this is rendering really badly. This is an example image from the Desert Fireball Network here in Australia. We have cameras that have about 40, 50 of these cameras across the outback, about 100 to 150 kilometers spacing. Just grab some water. To take pictures of these really bright shooting stars that have the potential to drop meteorites. So although you can see shooting stars fairly regularly, those are really small millimeter to millimeter size rings, things that have the potential to drop a meteorite, we're talking about centimeter to meter scale. So we're trying to basically find out where these are coming from. Here's a plot from about this time last year. I think there's about 37 meteorites on there that have these 37 meteorites that have an orbit, so you can kind of get an idea where they're coming from. If you can just about see in kind of a grey-green rim around there, that's the main asteroid belt. So they're not all coming from the main asteroid belt. And in terms of meteorite classification, this is a really nice plot. If you ever have a chance to go and dig into it, it's kind of looking at the geochemistry of all of the different meteorite classification meteorite samples. And what I want you to just get from this figure at the moment is that there's quite a lot of different types out there representing different types and parts of asteroids. As I was saying, the iron ones up the top here are obviously samples of cores and things like that. But the ones with crosses are the ones we have samples with orbits for. So we have a long way to go before we actually start filling in boxes of this whole area. And this, again, there's quite a lot of information on here. Quite like this though, it's looking at sizes of objects. So looking at maybe there's 10 meter sized objects here, going to smaller on the Earth, Moon, Mars, interplanetary, and what instruments can we use to actually get an idea of the numbers of these objects. So obviously at the larger sizes, we can use crater surveys on different planets. Obviously on Earth, we're a bit biased with erosion. We have InSight on Mars, which I'll talk about as well. So looking at the impact rate on Mars. And then we have these fireball networks and meteor networks going into these kind of smaller ranges. So in terms of sample return mission, we can say that, okay, the orbital origin is known-ish for sample return mission. Sample return mission. I say ish because obviously you know exactly which body you're going for, but all the bodies that we're sampling so far, there's been 3. I guess no, probably more like that. Some people say 5, but they're in near Earth space, so they've already been evolved from the main belt. So we don't know where they originated in the main belt before they came to Earth. Number of parent bodies, we can't sample very many, so a lot of effort to get out to one of these things. Can't bring back much material, costs a lot of money, but we do have very, very pristine samples. In terms of orbital meteorites, we can make an educated guess of where they come from. We can get these orbits, we can start doing statistics and modeling where they come from to get an idea of where they might have got kicked out of the main belt and how they might come to Earth. But the idea is that we can actually sample a lot of parent bodies. We can get very large amounts of material. It's basically how much survives to the ground, and it doesn't cost anywhere near as much. Obviously, contamination does vary, but the idea here is that if we can start getting statistically significant numbers of these orbital meteorites, we can actually get a bit more of the idea of what's going on in the solar system. So I'm the director of the Global Fireball Observatory. We have cameras networks around the world. The Desert Fireball Network is just the Australian branch. And we have partners all the way around the world. We have now about 15, we have about 1,500 orbits of these larger centimetre to metre size objects. And we have 14 meteorites we have collected. So that's actually about 25% of the current orbital meteorite collection. There's a few of them that I might talk about later on. So how do we actually recover meteorites? We take pictures from these different camera locations. The cameras, they'll come at some point. And we can, from the different locations, we can triangulate how this thing comes through the atmosphere. We can actually model its dynamics. This is where it's really useful to look at, and then obviously we can model things to the ground and find meteorites. But we're not just observing where they come from, potentially finding the meteorite, but we can also really well study how they come through the atmosphere, how they might break up, how they might fragment. The rocks that are on the ground are way stronger than what's at the top of the atmosphere, because for the stuff that survives is going to be much stronger than the fluffy stuff that actually hit at the top. Anything that's weak will have got completely disintegrated and protected. So our atmosphere is fantastic protector of us, rubbish for trying to collect meteorites. But I think I prefer the way it is at the moment. So then we can go out and do some meteorite searching. And Ellie Sansom here in Orange has done some fantastic work during his PhD on actually making this much less of an effort by bringing drones into the mix. So traditional searching was we go and stand out in a line, we walk along the desert looking for black rocks. And now with doing drone surveys, we've trained a machine learning algorithm model to recognize what are meteorites and what a background. And we have actually taken real meteorite samples out to train this on. And had a fantastic success a couple of years ago with this one here. It was observed by only 2 cameras. It was a really large search area. We probably never have gone and searched it by foot because it was just too big. 2 guns and we probably this was quite small as well. And I have to have a picture of a very happy James showing this work. So this is the meteorite that we recovered from that, which is awesome. Well, we do have quite a few still to recover. We've got about 60 meteorites on the ground from our 10 years of observations. Some of them are really quite hard to get to, but now with hopefully with the drone survey, we're going to start picking up quite more and start getting towards those statistically significant numbers for the solar understanding the solar system better. Something else we can look at is the spectra, not just of the asteroids out in space through a telescope. We can actually look at their spectra as they come through the atmosphere. Now, when they come through the atmosphere, about 95% of what you see in a fireball is the atmosphere burning rather than the meteorite. But you can still get an idea of what the rock composition might be. This is really ongoing work, trying to get spectra of these very rare, uncommon events without being able to point a narrow spectrograph at it. Most people have just been looking at meteor showers where they can just point it at a certain point in the sky and just hope something's going to come across. This is something that over the last couple of years, a lot of the all-sky networks have started to implement as well. And we have collaborators coming out in September to do that with our network too. And even if it doesn't drop a meteorite, there's still stuff that we can do just by observing how they come in. So this is really cool event that happened in Canada. We actually saw a rock that came from the Oort cloud, which is way beyond Neptune. And most people say that the stuff that comes way beyond Neptune is more cometary. It's fluffy, it's light, it's where all the volatiles went in the early solar system. There's no rocky material out there because all the rocky material condensed really early on in the early solar system. But we saw one, so it's showing that there is that mixing going on in these models. This on the left is just kind of having a look at where objects are coming from in the solar system. This one here, Alma-Sitta, is a nice event that, okay, there's a few different what we call resonances. So these are basically highways into the inner solar system. How do rocks get flung in? They can get flung in through these what we call resonances. And this one, we have maybe 2, possibly 3 options of where it might come in from, which are the ones on the inner side, from the inner main belt. However, there's some, this one, we really don't know. So by saying that we know where it comes from, we know it's from the main belt, but that's about it. So again, the more individual cases are a bit rubbish, but together as a whole, we can start piecing that story together. So going on to getting into strengths, how these things break up in the atmosphere can give us a fantastic idea of the strength of the body, and also how this is a really nice visualization from this paper on asteroids 2008 TC3. I'll come up to why this one is particularly special, but as the movie goes on, you kind of see that things are slowly breaking off and shedding from the outside. But at some point, there's a catastrophic explosion. So you kind of get an idea and a feel for how the lighter stuff comes off first, and then we end up with the much stronger material at the end. So although we don't get cluster craters on Earth, we can get what we call strewn fields. So it's not just one rock dropping on the ground, it's broken up into lots of pieces, and we can go and map where these different pieces are, look at their masses, and kind of get an idea of how it might have fragmented. So this was an event back in 2013, was before we had our cameras, but it was caught from satellites in orbit. And from a bunch of different techniques, including using weather radar, we were actually able to figure out where this strewn field might have been on the ground. And again, using the drone model, we were actually able to pick up about 88 meteorites so far, and we can get an idea of how this scatter. So each size of this just represents the mass of these objects. So there's a scale bar down here. This is one of the bigger ones, 1 meter across. And so this was in South Australia, but we can get an idea of how that scattering can really show a little bit more about the interior of the bodies. It's a busy slide, but what I'm wanting to kind of just show is that, yeah, going back to cluster craters on other planets. So Mars is a fantastic drawing board for showing you how these things can scatter in the atmosphere. And we've looked recently at about 500 of these cluster craters and how they scatter to try and look at trends of how things might be going on in the atmosphere. There's a bunch of different conclusions, but what kind of makes sense is that at higher elevations, you're seeing much more cluster craters because things are fragmenting and surviving to hit the ground. Whereas at lower elevations, things are probably still fragmenting, but not as much as surviving. So the cluster craters on the ground are much smaller. And how dispersed they are as well, further down, is much greater as well. So I guess confirming what we can see on Earth, but it's nice to be able to actually see the evidence on that as well. Still trying to look into the seismic, the strengths. What we can also look at is how these things behave in seismic and infrasound. I've got a slide a little bit further on. This is a fireball event over Earth in 2016, and we actually captured the sonic boom basically in seismic. This is just a little event. We can kind of see different wave patterns coming through there on the file. So let's see if I can click this. I'm not sure if you guys online are going to be able to hear this. I'm really sorry. Let's see if I can. get the idea. So this is the This is the SEIS instrument on Mars. It's the first seismometer that's been put on the surface of Mars, and it had a bunch of different science cases. One of them was to be detecting Mars quakes, trying to get an idea of the core, and last year. Let me play that again. So that's basically just saying that we can hear impacts on other planets, which is pretty cool too. And this is the graphic I meant to put first. Sorry about that. So when these things come through the atmosphere, you get acoustic waves coming down. Yes, you can get the impact. Probably not on Earth. They're way too famous. You can use something really big to be able to detect the actual impact. On other planets, we can do that though. But we sometimes can get the coupling with the ground, the sonic boom, and we can trigger seismic signal. What's really cool is if we're actually looking at the infrasound, which is basically low frequency sound. You can hear it, but also that it directly correlates to the energy of these objects as well. We can get the idea of their impact energy in the atmosphere. And we have set up a network, trial network in the Perth Hills here. This is in Bickley Valley of some infrasound sensors, trying to get, this is an example of fireball that we've heard in Bickley Valley. And we're really excited to probably be partnering with the Geological Survey to try and maybe put some of these out with their amazing WA array. And this is basically a man-made fireball. So back in 2020, the Japanese Space Agency brought back a sample and basically did a sample return mission to asteroid Ryugu. It brought back extraterrestrial material to Earth. But because we knew when and where it was coming in, it was going to be coming in as a fireball, we could go and put out all of our instruments. This is in South Australia. All the red dots are where we have Desert Fireball Network cameras in the area anyway. We put a few more in there, and all the blue ones are where we have these. We put it out infrasound arrays. We put a few seismometers in there. We also have the Australian National Seismic Network monitoring as well. Got some good results on that. And if anyone is interested or wants to help process that, because I don't have seismic expertise, I'm more than happy to get some help from that. But we do have some experts in infrasound, and they were actually able to measure exactly when the shockwave stopped in the atmosphere. So with that shockwave coming down, it creates a cylinder basically as it comes down to the ground. As it stops, is no longer in hypersonic flight. You actually get a spherical shockwave coming out rather than a cylindrical. So you can actually measure where those two interact and figure out where it ended its hypersonic flight. So kind of going back to what we're trying to get at, that moving on more, I guess, to modeling and predictions. We talked a little bit about how we can characterize asteroids and basically fireball networks and all these different aspects of it, from seismic to infrasound, can really help start informing asteroid characterization for planetary defense. Looking into the modeling and predictions, that's something that really only fireball networks can do. So when we're looking at where things are coming from in the asteroid belt, this is kind of, I'll explain this a little bit. So this is looking at the size of an asteroid. So here we're starting at around 100 meters, going up to about kilometer sizes. Each one of these colors is saying where these objects coming from in the main asteroid belt into near Earth space. How did they get there? Now these are, so again, 100-meter to kilometer-sized bodies. They're coming from different areas of the main belt. So each one of these is a different highway into the inner solar system. And you can see it's different for different sized objects. what's happening down here? We're still talking about this residual risk area down here. This is 10 meters. It's still a risk to people and infrastructure. And what we're looking at with the Global Fireball Observatory and Desert Fireball Network is these sizes, centimeter to meter sizes. So we're actually looking at this area in here, and we can start informing this. So rather than just extrapolating down from the big sizes to the small sizes, where I can tell you, spoiler alert, doesn't match what we're seeing with the fireballs. So something in the middle here is going on, and we need to be able, and fireball networks are really the only way to start filling in that gap. Something that's just a little bit of a side note, and I guess going toward that linking meteorites with asteroids is how many asteroids we've actually, or meteorites, or fireball bolide events that we've seen as asteroids before they impacted. Now, if I was giving this talk 5 years ago, or 10 years ago, I just said, well, one. And now we've had quite a few. You can see the dates here. Getting stacking up. We had 2 last year. We've had 1 this year. And these were actually captured by the Catalina Sky Survey before impact. Someone tweeted about it, and a bunch of people went out and took pictures of the beautiful fireball that came down. And this one actually, sorry, this is a slide stolen from a talk that I gave a few weeks ago. And they recovered, they haven't recovered a meteorite from this one. It actually, I think, landed in one of the Great Lakes here in Canada. Yeah, it's right on the shoreline. All the small pieces are definitely in the lake. They're still trying to decide if they go out and go for a swim or not. This one in France was another one that happened earlier in early last year. Sorry, this is the early, yeah, this one was early last year, and they have recovered a meteorite from it. So we actually have the asteroid observations. We can start looking at the asteroid spectra of these objects and looking at the meteorites. So starting to bring these 2 sides together. And something that we're hoping with the Desert Fireball Network, in particular, down here in Australia, is this observatory that's coming soon. Looking at first light middle of next year, middle to end of next year. Vera Rubin Observatory is based in Chile, and it's going to be able to see a lot of near-Earth asteroids. It's going to be the number that we're going to be detecting is going to significantly increase. And the Desert Fireball Network is the only fireball network in the Southern Hemisphere that will then be able to see the objects coming through that it will see. So hopefully we'll start piecing those together, and we might get maybe 1 or 2 a year that we can match up. So that's pretty much big picture aspect. This is quite an old video now, but I'll leave this playing in the background while I take some questions. This is about 1,000 fireball orbits that we have from the Desert Fireball Network up until 2017. So we've almost doubled that now, and I need to update this. But thank you very much, and I'll take questions.
So with the, so with the cameras pointing up that are looking for the fireballs, stars, people manually reviewing their like each day for the previous night, or is it automatically detecting when it goes through?
So the question about the automation, I don't know if people online heard the question, I'll repeat them back. About the automation of our cameras. Yes, we are, this is pretty much almost fully automated. There's a few manual steps still in there, but you can't do that kind of an area manually. That's where, so fireball networks have been around since the 60s, and there's been 4 major networks kind of established over that time period. Each one has recovered 1 meteorite, but everything was done manually. Some of the stations were even manned, and they were on photographic plates. They needed to be recorded. It was a lot of effort. People moved to, this is one of the first ones that kind of moved to digital. But then obviously you need a massive processing pipeline behind it. And that's actually why, although we've been running for around 10 years now, we're actually only starting to get into maybe the 2nd or 3rd year of actual scientific or mining the scientific data, because it's taken us that long to actually develop the pipeline to process the data. But what we did do was get the cameras out early. So they've been recording, all that data is there. And now that we can process it, we can start actually exploring the science behind it.
Cluster impacts, largely clusters of meteorites that are broken up in the atmosphere, or is it from the exploding fragments that after
We're talking about the strewn fields and the clustered craters on different planets.
Yeah.
Yeah, so it's pretty sure nearly every single one of them is from atmospheric breakup. There are a few cases where you can have a double impact event, and those have been modeled and they're actually quite rare. So what we're seeing on the ground from cluster craters on Mars is one object that's broken up in the atmosphere, maybe not just one breakup, we might have had multiple breakups, and we can call this like almost a waterfall effect, where at some pressure of the atmosphere, the strength is exceeded, so it breaks up maybe into a couple of pieces. It gets deeper in the atmosphere, and that atmosphere is getting thicker. That pressure then increases more, and the next level of its strength is reached, and it breaks up again. So you kind of get this cascading effect as you come through the atmosphere of breakup in the atmosphere. So it can be one or multiple events. And from the cluster craters on Mars, we don't necessarily know how many breakup events we've had. When we can see them with our fireball network, we can look at brightness as it's coming in and get an idea of when something breaks up, you have an increased surface area, so the brightness increases as well. So we can get an idea of when those fragmentation events happen in the atmosphere. And actually what's interesting is because you know what's the properties of the atmosphere at the height of breakup, you can actually translate that almost directly into a strength in megapascal on rock, which is pretty cool. Yeah.
Yeah, just so online people can hear. So I noticed that the fireball network has picked up, like there's all those meteorites that you've seen sort of come through the atmosphere, and you have a vague idea of where they are, but you physically can't get out into those remote locations. The museum goes out into what quite often and ends up being the repository for all the meteorites that land in WA. Do you want us to look, or is it better if you guys go out and map exactly where they are, or?
No, we've got, depending on how they come through the atmosphere, our search area could be quite condensed, and some of them can be quite large. It really depends, I guess, on who's going where, and definitely keen to have volunteers help out with searching trips. If you want some of the areas like the Nullarbor that we go out to quite a lot, see there's nothing there, so it's fantastic for drone searching. Some areas you actually have quite a lot of scrub and quite a lot of trees, and you still have to search quite good. It's the only way. So I guess our limitation of recovering these things is manpower, and that's why we've gone to the drones. But yeah, happy to take help.
Hi, Ellie, that was a really fun talk. I'm quite surprised to see your slide that showed the meteorite types and which ones have orbits determined from the recovered meteorites. I was surprised that no iron meteorites are on that list. I would have thought iron meteorites are stronger than the stony meteorites and might survive coming through the atmosphere.
Yes, they're very rare. They come through, they're very rare events in terms of how often they actually would come through the atmosphere. There is one. It was published on Monday. There's 9 meteorite with an orbit, but the frequency of iron meteorite impacts is probably, I think it's around 2% of the objects coming in. So
does that mean that 2% of the 65,000 meteorites are irons?
No, not necessarily, because obviously they're survival, so they're actually easier, and there's a collection bias, a really large collection bias in our meteorite collections. So iron meteorites will survive longer on the ground, but also not only survive longer, but they're more recognizable still as meteorites thousands of years later. Not just from the weight, as it's saying, but also from you can I guess you can still crack, open a chondrite and you can say that, okay, it's got chondrules, this is not from Earth. But a lot of the rockier types of the achondrite and stony material, as soon as they've lost that fusion crust, so when these these objects come through the atmosphere, they're burning up, they end up with this black outer shell that's very thin. It makes it very distinguishable as a meteorite on the ground and you go searching when they're fresh. But the older they get, the more weathered they get, they lose that fusion crust. And they look just like an ordinary Earth rock, so they're much harder to distinguish as a meteorite. And if you're doing it by metal detecting, which is how a lot of meteorites do get recovered, you would notice an iron one, but probably not a stony one.
How is it known that only 2% of incoming meteorites are irons?
I would probably ask Bill Bland. I think it's the way that they managed to debias that of the collection.
I mean, is this a spectral observation? Or is this something, some assessment of rocks that are in our collections?
I think it's still an assessment of the rocks that we do have and trying to take that collection bias and the area that we've searched and the age of the areas we searched into account as well.
Okay, thanks.
Sort of following on from Aaron's question in terms of irons versus not irons and seeing more irons. And when they come through the atmosphere, do they look any different?
That is a very good question, and that's something with that I guess the spectral surveys are trying to get the idea of adding spectra to these observing these fireballs. What people have tried to use before is the color of the fireball. And there are a few studies out there that are trying to distinguish what the meteorite or meteoroid might have been made of just by the RGB image. So we're taking all sky images red, green, blue, and people say, oh, maybe if it's super, the one I get from the media all the time is, oh, there's a really green fireball. What's the green mean? Does that mean it's really iron? But that's actually because, again, 95% is the atmosphere burning. It's actually just telling you the property of what height is going through the atmosphere. But with the color, the idea of trying to get an idea with color, the conclusions of those were that, no, you can't unless it's an iron. Irons are the only ones you might be able to distinguish based on color. But again, still quite unsure. But hopefully with these looking at this actual spectrum of fibers that they come in, you might get a better idea of that and get a better idea of actually what is the percentage of iron meteorites coming through the atmosphere.
So the orbital iron meteorite that was seen, I'm guessing there's nothing anomalous about its fireball. From
I
testing.
haven't read the paper yet.
Okay.
It's on my to-do list earlier in the week. But
I might go find that paper. So.
I'm trying to remember the events around that one. It wasn't observed by a dedicated fireball network, I don't think. No. But it was, it might even have been a daytime one, but I cannot remember, and I really should. So. It's just. Any geochemistry questions for non-geochemists? Okay, it's Nick.
Actually,
I'm going to ask a question that I should really know the answer to, or several questions, but they're linked. From the desert fireball network, so the Australian network, how many events do you think have dropped a rock that you have now calculated where to search for? How often do you go searching? And who do you contact to get involved? I'm just asking on behalf of people who might be out there.
So we have, out of the some almost 2,000 events we've seen, we reckon there's probably about 50 we've got rocks for on the ground that are larger than around 10 to 50 grams. So depending on the search terrain, you probably might not go looking for something this big, but if it's another ball, you probably would go searching for something this big. All of the ones that we have recovered, you notice on the slide were the larger events. We've kind of had a collection bias of our own. The bigger, brighter events, the ones with the more likely to find the bigger mass, are the ones we have gone out searching for. In terms of how often we actually go searching, at the beginning of the project where we had lots and lots of people involved, we'd probably go out 2 or 3 times a year. At the moment, there's two people running most of this in the background. And we haven't been able to get out for a while, but we're going to do with the drones, get quite a lot more out. We've got a discovery project recently that's looking at trying to fund quite a few more search campaigns, especially using the drone to recover much more of these meteorites. And probably send me an email, and I will add you to our list of volunteers that we ask about. We're actually geoscientists who have field experience. It's fantastic pool of people to be asking. That's usually what we're worried about, is taking people who've never been in the field before into Melbourne when it's about 30 degrees, or even just asking them to camp in tents for 2 weeks. So, yeah.
What are the numbers of meteorites that are entering the Earth's atmosphere, say, per day?
Well, that's actually something that we're trying to get at. I kind of focused a lot on the properties of these rocks, but something I'm actually really interested in is that what we call size frequency distribution, is how many rocks are hitting the Earth at different sizes. So we have an idea of the bigger ones. We have a really nice idea of, I should have stolen that. One of your other links from today. So we have kind of what we call it, so size frequency distribution, with larger objects on one end, smaller objects on the other. There's the amount that are hitting the Earth. This very large end is every kind of, like I said, with the Telebits one that was 20 meters across, maybe every 30 to 50 years. As we come down to smaller sizes, you might expect to see something around the size of a meter hit the Earth somewhere on the Earth once a year. But we don't really know the numbers that we have for the really large stuff, the asteroids, in the main asteroid belt. If we're actually looking at the slope of their size frequency distribution, it doesn't match the ones of the smaller ones. So somewhere in there, we have something going on, and trying to match those up is something that we're trying to do through our observations as well. Any questions online as well?
Don't know, no question about mine yet. So kind of on that sort of same point, has anyone ever done like a sort of, I suppose, like a controlled quantitative survey of like micrometeorites? So like I've swept rooftops for micrometeorites before, and you get so many on a certain size rooftop, but then if you did the same rooftop 10 years later and you counted how many, you sort of have an average of how many micrometeorites have fallen in that space over a 10-year period. Do you know if anyone's done something like that before?
Don't really ask that question. I know there's quite a lot of people who do micrometeorite studies. I'm not sure if I don't know if anyone else, do you know anything about frequency of those?
No, but top of it.
Nick?
I know someone who's trying to do that from Antarctic ice core,
Yeah, okay.
and separating micrometeorites from them. It's incredibly hard and very time consuming.
I do know on the size frequency plots, often at small scale, there is some data that is related to micrometeorites, which is then populated next to the other weird pockets of data that could be. So I think there is.
The other kind of observational data we have that I didn't mention that is quite important, that does also help fill that gap. Yes, ground-based fiber networks are pretty much the only ones. But there are a few satellite networks that can also see fireballs as well, which is pretty cool. And those are becoming, I won't say more common, but there's a lot of more satellites up there that we are being able to use and acquire data for planetary science purposes to try and get a better idea of these frequencies. The really fun one to go and have a look at is the Centre for Near Earth Object Studies on the JPL website. It's for fireballs, and it will show you a plot of all the fireballs that are over 0.7 kilotons of TNT impact energy equivalent. So these are the really big ones, the kind of meter plus size, or meter size plus sizes. And this is actually a network of satellites around the world that was set up by the US to detect nuclear explosions and rocket launches post World War II. So, but it does see fireballs, and Chelyabinsk is the largest event that it has ever recorded. So it's been recording for about 30 years. And the one over Queensland around back in May, I don't know if anyone saw that in the news, there was a really big bright fireball over Queensland that people got quite excited about. And that's probably in the top 10 largest impacts that have ever happened on Earth in the last 30 years as well. So that's another way of trying to get that planet scale detector of these larger events. So yeah, you can look to the moon for those. Basically, they're so rare that you need planet scale detectors. So we can spread our fireball network around the world. We can also look for orbit too. So maybe just need to put a few more fireball camera networks on future plans.
Also, Bill Blank commented that math energy and authors, including Luigi Folker at IC, has done a large database of micrometeorites that I understand.
So that's with a really nice different types of meteorite plot that I showed is by Matt Genge, and I know they've done amounts of micrometeorite studies. I just think that they've done size frequency kind of ideas. But, yeah. And fireballs from interstellar objects have not happened yet.
Oh, come on, now didn't one fall off PNG? And what's the professional view of the event in terms of magnitude it's supposed was initially interpreted as?
So this was an event that was only observed by these US government satellite sensors. They are excellent at getting the impact energy of these events coming through the atmosphere. They're pretty rubbish at getting where they come from and their speed. So it's actually a hidden slide on here, but we had an event that the US government sensors saw and we saw with our network. It put it as a trans-Neptunian object. We have it as something they felt. So I would say just from that, obviously it's a fantastic resource and we use it a lot, especially when we don't have other observation data. But to say that something is from interstellar origin from that data set is probably a very big leap. Probably would only be able to prove it if you actually picked up a rock that was massively different to something we've ever seen before. But the actual event itself, very unlikely anything actually survived that kind of size explosion at that height. So again, that height would have shown how strong that object was, and probably not much material would have survived, and it would be really small fragments. So yes, if you're going to go and trawl bottom of the ocean to look for really small fragments of meteorites, you're probably going to find some, whether they come from that event or not. We'll have on my overland next time.
No more further questions online, I think. All right. Thanks very much for the amazing talk, Ellie.